Okay, so the topic we're getting into is about volumes. So what we have been working on a lot is areas. And so this is just a little screen showing you what we've been doing with Riemann sums. This is the curve y equals x squared. And there's three rectangles here trying to find the area. So our integrals were just adding up our width times our height, and our width was delta x and our height was the f of x. And the idea was the integral would make an infinite number of rectangles, and as you get more and more rectangles, you get closer and closer to the actual area, so that even if I made just 40 rectangles here, that's almost dead on that area. And you can see what the Riemann sums are giving 8.999, and their integral gives you 9.0. And so that's what we've been working with. So we're going to change it. We're going to add a third dimension. We're going to try to find the volumes of some objects. So to find a volume, there has to be something that comes off the paper, out of the screen, a third dimension that comes at you, because we can only draw 2 dimensions on paper. And so I'm going to use some animations to kind of try to show you these, the third dimension. So they have to give you some clue on the third dimension, because you can't draw it directly on the screen. It has to come out. So they're going to tell you something about the height of what's happening. So what we're going to start with is we're going to try to put, we're going to work with cross sections. And so I'm just going to show you an animation to show you what we're going to start with. So this animation is about putting squares under a curve. As you can see, it's just like building those rectangles as you go across, but these things, not only do they have a width and a height like the rectangles we've been working on, so down here would be the height we had been using, and then the width, our little delta x, but now they have a third dimension that comes right on out of the screen. And so what we're going to use is our f of x, our curves, the things that we've been using, are going to be the bases of all these solids. They're going to be the bottoms. As you can see, this solid was sitting on that, under that curve, and then the squares are being built up. So the key for this is this one. They particularly told you that the cross section was a square. And so what the cross section means is as you look through this, if you looked through this object, you would see a bunch of squares, and they would be telescoping smaller and smaller or bigger and bigger. And so we're going to talk about how we are going to try to draw that on the paper, and then what we're going to have to do to calculate the volume of this solid that we've now created. Okay, so I'm going to go over to the notes, and you should have this packet. And so we're going to start just with one curve. And so you can see we're going to go from A to B, and we're going to try to put in a solid whose cross sections are squares. So right now you see that representative rectangle that we've been working with so far. And what we've done before is we called this was delta x, that was our width, and then our height was f of x. And all we did in 2 dimensions to find the areas, we added a bunch of them as we went from A to B, and we added them all up. Well, to get the third dimension, I have to tell you something. So I'm telling you that these cross sections are squares. And what that tells you is that the dimension that comes out of the paper is going to make a square. Well, it has to be the same length as this to be able to be a square. And so I'm just not a very good artist, but I'm going to attempt to show you how it would be in 3 dimensions. So I'm going back to elementary school to work on this 3-dimensional box coming out of the screen. So what I need you to see is that this distance right here, this edge right here, these are coming out of the paper at you. So those are the things raised up. Where up here, that would be this dimension right here coming up off of the paper. Okay. So when we did this as areas and we just had to add it up, we added up from A to B, and we added our base times our height, or delta x there, and we called it, that was area. Now we have a third dimension, and so we have to figure out what this third dimension is, and the third dimension is this thing coming out of the paper. And how long this is, since it told us that they were squares, this distance right here must be the same distance as right here to make a square. So then this distance must be f of x as well. So when we add up the volumes, the integral is still going to add things up, but when we add up volumes, now we have f of x times delta x, where we can write f of x squared times dx, or delta x. So that will give us the volume, adding a bunch of these up. And so you saw on the animation what it looks like when you add a bunch of them up. They obviously are all different sizes, and that's what leaving it as the f of x does. The delta x is this little dx, the width of each rectangle, which is, with the integral, infinitely small, so that we get a ton of them as we go across. Okay, but there are lots more shapes that they can be. So the cross sections can be right isosceles triangles. This one's a little bit harder to draw. And so the base is still going to sit on this paper. And so this distance is f of x, and this one's delta x. But somehow this thing has to come out of the paper so that we create a right triangle out of it. And so I'm going to attempt this triangle. Okay, and so what you need to get out of this drawing is this is the side coming out of the paper at you. Okay, so that's coming off the screen at you. So again, when we set it up, if we had to add up a bunch of these, we went from A to B. And when they were just rectangles and we were doing area, we did f of x times dx, or delta x. But now we have this third dimension, so we have to find the area of this thing. Well, if there are going to be a bunch of triangles, we know the formula for the area of a triangle is 1/2 base times height. Well, of this triangle, I'm going to go ahead and outline the triangle here that you should see as a cross section. The base is f of x right here. The height is coming out of the paper at you, so it's this distance right here. Well, I have to tell you something about that because you're not supposed to just be able to look at the screen and tell you. So I told you that it was an isosceles triangle, which means two sides are the same. And since it's a right triangle, this length right in here is the hypotenuse. That can't be the same length as the two sides. So this must be the isosceles side that's the same length as the base right there. So when I put this formula in, the area of that is 1/2 f of x times f of x. Okay, so that would just be the triangle, but to make it a volume, that's just area, you have to add the third dimension, which is our delta x or our dx. So when we put this in our integral and we add up a bunch of them, we're going to have a 1/2, and we're going to have f of x times f of x, or f of x squared. So another way of writing this that we worked on was that you can put this 1/2 out front. So I do want you to look back at something, compare the triangles to the squares, and it should make sense that the volume of this shape is going to be half as much as the volume of the square, because to make the right isosceles triangle, we just had to cut that square in half, and that gives us our triangle. Okay, we're going to do two more shapes with cross sections. One is rectangles, and so rectangles are very similar to squares. But the difference between a rectangle is that the height and the base are not the same thing. The two dimensions are not the same thing. So you're going to have to be told what the height is relative to the base. Otherwise, you're not going to know that. And so it says whose height is twice the base. So I'm going to repeat what I did for squares to try to make this shape. But the height is twice as long as the base now, so it's going to be even taller. So this is the height that's coming out of the paper at you. That's the dimension coming out of the paper. So once again, this is f of x, and this is delta x. But we have to know how long this distance is, because if we're going to find the volume of this, we have to know our length, width, and height for this. And so since it says the height is twice the base, this side must be twice f of x, because f of x is sitting on the base of our shape. It's sitting down here. And so that's just one of these, and if we add up a bunch of them so that we can find the true volume, we would go from A to B of f of x times 2f of x times delta x or dx. And again, we can definitely rewrite this and bring the 2 out front, just a number, and put the f of x's together. And there's our equation for the volume of this rectangle. Okay, the last one are semicircles, cross-sections that are semicircles. So the shape that we're putting in here is a semicircle, and you have to remember that this rectangle is always the base of whatever shape you're doing. So we have to have cross-sections that are semicircles, which means if you looked through the volume when you were done this way, and it's coming out of the paper, you would see semicircles. So the way we're going to do this, show this arc twice. So now if you're peering through this, and keep in mind the paper is the base, and you're looking through, you should see half of a circle. Okay, well, we have to know our dimensions. So this distance is still f of x, and this is our delta x. Now, the dimension coming out at you, which is in blue, that we also have to know, but what we should know is since it's a semicircle, what's coming out at us is a radius of the entire circle. Well, then you also have to realize that that is also a radius of the circle. So from the center this way or the center up, out at you, that's also a radius. So when we write our equation for this, we would have a semicircle, which would be 1/2 and then pi r squared. That's all we'd have to know for a semicircle. Well, we see that our radius is not f of x, it's half f of x. And here's where you have to be really careful when you plug this in. Because if we went and plug this in, we'd have 1/2 pi, 1/2 f of x, and that radius would get squared, which means the 1/2 gets squared as well. So if you end up simplifying this, this 1/2 in here would get squared, and then we'd probably put it together with the 1/2 out front to make a 1/8, because 1/2 squared is 1/4, times 1/2 is 1/8. We'd have our pi, and we'd have f of x squared. So that would give us just the semicircle part. That would just give us this area of the semicircle right there. But we have to add the third dimension to it, which is our delta x, to give it a volume. So when we write the equation for adding up these semicircles, we'd go from a to b, and we'd have 1/8 pi f of x squared, and have a dx, for delta x. And again, like last time, we can move numbers out front, and pi is also a number. And so a lot of people like to combine this as pi over 8 instead of writing 1/8 pi. Go from a to b and have f of x squared. So the key with these volumes is to identify what is your shape and what is the formula that governs it. Something I want you to get down as you simplify this is they're going to tell you a shape. And so how you write the equation for the volume is simply the area of the shape times the thickness. And a lot of times, right now especially, our thickness is going to be our delta x. We will change it to a delta y at some point, but right now it's a delta x. So then we just have to go with the shape. So when it was a semicircle, we had 1/2 pi r squared, and that's what we put next to dx, or delta x. When it was a rectangle, we did base times height, f of x times 2f of x. When it was a triangle, we did 1/2 base times height. And so the base was f of x and the height was f of x, and we did 1/2 of those multiplied together. When it was a square, the area of a square is side squared, and each side was f of x, so we got f of x squared.